All right, and we're recording. So, if we're okay, thank you everyone for coming. So, it's 15 minutes, Yanzhi. You can start in a moment, and a real-time visual odometry using 3D feature lines from stereo cameras. All right, off you go.
Okay. So good afternoon, everyone, and welcome to my presentation. And so, first of all, I'm showing the result, the overview of my poster. And as you can tell, there are 6 parts in total, and I will introduce them like in the following slides. So my project is about to design a novel real-time 3D visual odometry algorithm that could apply the track 3D lines from the serial videos or the sequential images, and then with the velocity input, it is be able to provide a robust and a relative computationally cheap observer, and then to estimate the odometry. So as for the motivation, to solve the navigation problems in the field of the autonomous robot, visual odometry and visual slide is introduced and become a very popular field of research in recent years. And the motivation of this project is to fill the gap of the feature line-based visual odometry in an equivalent system. More specifically, typical visual odometry methods are based on point features. It tracks the point in the sequential images and then reconstruct the movement of the points and estimating the camera pose with a relative complicated method such as a perspective endpoints. Well, however, the point features are sometimes it's hard to track in low texture environment. So on the other hand, the live features is more reliable in such low texture environment, and the live feature has the natural advantage of a higher geometric expressiveness compared to the point features. So for the equivalent kinematic, the key advantages are that the equivalent, the observer is relative computationally cheap, and it is robust when dealing with the drift of the word frame. So in this case, it's quite important to research a live feature-based visual odometry in an equivalent system. So for the background of visual odometry, so since GPS is now working in outer space, so visual odometry was first designed for the outer space navigation, especially for the Mars rovers. And back then, the visual odometry was first named as ego motion estimation, where the ego motion means the 3D camera motion within a certain environment. So in 2004, Nasser and his colleagues first introduced the term visual odometry, where they present a robust camera motion estimation algorithm based on the video input. And visual odometry was soon become popular in the field of robot navigation. So the problem for this project is quite straightforward. So I break down this into 2 parts. So the first part is to identify the 3D lines. And the second part is to build an equivalent kinematic system and design an observer on it. So for equivalent kinematic system, some key preliminaries and notations are shown here. So first, for the light presentation, the lines are represented in Grassmann 4x2 space, where the Grassmann 4x2 takes 2 points that lies on the line, and with additional scale factors. So for computational convenience, I say the both scale factors 1. And the system state is then composed by the transformation matrix and the lines. So it belongs to a mean for m, and where m is actually 3 times Grassmann 4x2 powers to n, where the n here is like how many lines is detected in the environment. And the velocity of the state is speed matrix u and a speed of li speed matrix vi. And this belongs to a space v, where space v is actually 3 times x to the power to n, and then the leaf cx is designed to be p and qi, where it's in space g and it's actually 3 times x to the power to n. And then the maps phi, psi, and the linear function f and leaf function lambda has the following structure. Note that the g here, the minor g here, is not same to the space v. It's more like a tangent space of the capital G or the logarithm of capital G. So as for the project deliverable or the project scope, so the key deliverables are a equivalent kinematic model and a relevant observer on the 3D feature lines, and then a 3D feature line tracker and Tyson algorithm via simulation. So the Tyson rule that is a stretch goal, so it will discuss in the future work later. So the front end of my visual adoption algorithm is a 3D feature light tracker. As you can tell from the workflow diagram, lights in stereo images are first detected by the LSD, which is a light segment detection, and a half-light detector, and then matching those lights in by patch matching between stereo images. And a core algorithm applied here for the light tracking is called the circular match. So, for example, consider we're currently matching a point, the light number 3 in the top left image. So first find a point A around here, and then matching using the epipolar geometry to find the corresponding point B in the right image, and then with a certain tolerance of the image set, like the 10% of the image size, to find the corresponding point C in the bottom right image, where the bottom image is like the neighbor frame. So, and then once the point C is found, and then using the epipolar geometry again to find point D as the bottom left image, and then matching back to the point A. So the tolerance is not fixed. It's like depending on the camera speed. So if the camera is moving too fast, then the tolerance should increase accordingly. And so the overall process is about A matches to B and matches to C and matches to D and matches all the way back to A. So it's that is why it's called a circular match. So as a result, you can see that the light number 2 in top image is matching to the number 7 here, and then 3 matches to 2, and then the 7 matches to 3, and 10 matches to 1. So for the equilibrium kinematic and the observer design, so I followed Zhao's observer design program, and the system kinematic and the leaf kinematic is shown here, with the map phi side and I've lambda defined here. So the architecture of the observer is shown here, where the observer takes the velocity input and the measurement as input, and then construct a leaf state, and then using the estimated leaf state mapping back to the original state to estimate the odometry. So the error function here is determined by a cost function. So the task is to build a innovation delta function to make the cost function decrease. So we have made a few approximations here. So the delta function looks like something like this. And the simulation here, assuming 3 lights being observed, we supply noise on the velocity and input and the light measurement. So the total simulation time is 10 seconds with a time step of 1 millisecond. And the blue one is estimation result, and the red one is the ground truth. And so the black star here is the configuration output, which is light measurements Y. And as the light figure shows, the overall odometry is quite satisfying. However, the light converging is not like slightly converging to the ground truth. So the leap node of the observer is the performance is here. So as you can tell, at the first 2 seconds, it converts very fast, and then at the 10 seconds, convert like very, very slowly. So as far as I consider, it's possibly caused by the approximation we have made when designing the innovation function delta. But the overall performance is okay because it's decreasing. So as a conclusion, the performance of this observer are mainly depending on the noise level of the velocity or the light input. So the current innovation function has a few approximations, and future work will be redesigning a more proper innovation function, a better 3D feature light tracker, and testing on real data. So the plan for the test on the real data could be either using data set from online, like the Europe data set, or build the algorithm on the embedded system with an IMU to measure the velocity. And I think that's pretty much I would like to share for my poster. So in the end, I would like to thank Zhao and Hang for supervising me on this project. And I would thank all of you here for your valuable time. And please feel free to ask any question for my poster.
Very good. Well done. 5 minutes and 30 seconds left. So.
Okay.
So let me ask with the questions, or start with questions. So in, I think your conclusion slide,
Yep.
you say that the current innovation function has a few approximations. So what approximations are you making? Could you give me an indication of that?
Yep, sure. So back here, so as you can see the cost function here. So by taking the derivative of the cost function, and Han and I find it is hard to derivative for some terms, and so those terms are really doesn't matter for the overall performance. So we decided to just ignore that, and we have something like this.
Right. So there were approximations in the differential of the cost.
Cost function, yeah.
Which is C, right? That's a C there, is it?
Yep.
You managed to make that cost function so small that I can't see it very easily, but
Okay.
nonetheless.
Yeah, sorry, I think I can enlarge it.
No, don't worry. No, don't go
Okay.
there. Don't change the scale. That's
Okay.
All right. Well, I'll have a look through your thesis on that, yeah, and see.
Yeah.
That. Yeah, that one makes sense. The convergence. Show me the convergence again.
Yep, here.
The next slide, I think. Your results slide. Yes.
You mean this?
In the right-hand side there, you said that it's converging very slowly towards the end.
Yeah.
Is to go back to the previous slide? Yeah. So do you, that sort of convergence you're looking at, do you know what that convergence would be called?
So you mean like why this is like converted slowly in the
well, it's a particular sort of convergence, right?
Yeah.
So that looks to me like an exponential convergence, right? That's essentially an exponential there, which is very similar to a linear system will converge like that.
Yeah, but actually, I think that is caused by the innovation delta here, because here where so the delta function and apply to the update of the libc, and the performance is like a exponential function. So the overall like the structure of the lib node here is like a exponential. So I think that's probably the reason why it's converged slowly in the last few seconds, and why it's look like this.
Yeah, I mean the Lyapunov convergence looks good to me, and it's almost surprising that the lines haven't converged. That would be my interpretation of it. But would you hazard a guess on why the line estimates are not converging as quickly as the state?
So that's probably because of the noise, because when like in the first few seconds, and the estimation is very rough and the noise is very rough, so the and in the last few seconds, so the convergence is like converging to the ground truth, adding the noise. So the noise is fixed. It's fixed for like each in the simulation for each line. So it's probably converging to the line, original line plus the noise instead of the line itself. So, and that's why I conclude that the performance of this observer is depending on the noise level of the model input, or the line input.
The simulation you showed us doesn't look like there's any noise involved, right? If you look at that simulation, I don't see any perturbation in the trajectory.
Well, actually, it does have some noise, because if it had no noise, then the ground truth and estimation is like, well, finally like meet together, and so
noise measurement.
Yeah. So there is some errors, some noise, but the noise is like I said it as quite small, so it looks like something like this. And for the line measurement, so the line and sometimes the line is not sorry, I that's a question, and I have asked myself as well. So for the line measurements, sometimes it like converging to another state. I think it's probably something like another like solution for the system. So it shows the convergence of the line, but it's not converging to the ground truth, it's converging to another line, something like symmetrical here.
Did you, I mean, this is my last question. Show me the period of time you ran for again on your Lyapunov function, the decrease.
So you mean
that one? Yeah. So that simulation has been run for 10 seconds.
Yeah.
Have you run a long simulation? Have you run 100 seconds or 500 seconds?
Yeah, actually, I have run like 20 seconds and 30 seconds. Well, the 100 thing is like taking too much time, so I just run 20 seconds.
So you've gone up to 20 or 30 seconds.
Yeah.
Did the Lyapunov function continue to decrease?
Yeah, it is continuing to decrease, but like, so for here it's a 0.001 and 0.0132 whatever.
Yeah,
and,
it gets very,
it's just why we're like just, so the 20 seconds is about 0.0132175, something like that. So it's like, it's still converging, but it's very, very slow. Like.
Yeah, okay, yeah. All right, any other questions? All right, so thank you very much, Yanzhi. Excellent. Okay.
Thank you.
So I will stop recording.